Hello, I'm Dr. Harper. This video is a lecture video in business forecasting. So let's bring up the notes. In business forecasting, there's some terminology. First, time series forecasting has to do with patterns within a series, a time series, and we capture those patterns and forecast the future. A time series is a business data, business variable over time. Causal forecasting would be variables outside or exterior to the actual time series, and those variables are used to forecast the time series. You'll also have qualitative forecasting. You'll have different qualitative methods and techniques. We will not cover those in this lecture. There are quantitative techniques, and we will cover those, some of them. We'll cover it over here: moving average, exponential smoothing, regression, seasonal indexes, and we'll put them together. Finally, a terminology of intrinsic forecasting and extrinsic forecasting. Intrinsic forecasting is essentially the same as time series forecasting. Information patterns within a time series will be used to forecast the time series. Extrinsic forecasting is the same as causal forecasting. Information extrinsic or outside the time series that's causing the time series, that's an extrinsic or causal forecasting. This table here, I start with a 3 by 4, 3 rows, 4 columns, 3 different time series. And the columns represent terminology: stationarity, components, and techniques. Stationary is the overall nature of the time series. Components is a cause of variability. And the different techniques we will cover on 2 passes. The first pass I call my introductory examples of these 4. The second pass, I go through these techniques and go deeper and pull out other terminology. In a non-stationary time series where you begin combining components, you can solve these with blocking or filtering, and advanctions and extensions would be ARIMA models, autoregressive integrated moving average models with box-Jenkins techniques and spectral analysis. We will not do that in this lecture. However, I will come right to this point, and this would be further analysis in forecasting. And finally, I have a 5-step problem-solving process in forecasting. First, always plot the time series to determine the stationarity. Second, choose your components. Plotting the time series and choosing your components pretty much go together. Once you have the determination of stationarity, you've chosen your components, then select your technique. And here's where people make mistakes. They first start with a technique, and that technique may not be the right technique over here for a certain set of components of stationarity. So first determine what type of time series you have, what type of components you have, and then select your technique. And then estimate your parameters and then obtain your forecasts. So let's do the first pass through this table. The first pass with my introductory examples. Introductory example number 1 is moving average. Here's the 5-step process, and assume we have a weekly time series. Now, what a weekly time series means is that we have 8 weeks worth of data, and every week our time series is aggregated over a week. So you might have this time series might represent sales in dollars, maybe the number of homes sold in a real estate agency. Maybe it's a number of calls coming into problem calls coming into a switchboard. It might be the number of people that have been serviced that week, or how many jobs that came in that week. But this number is a weekly time series that's aggregated over a week. Also, these numbers are not just numbers. They represent some reality behind the numbers. They're just a representation. Okay, the first thing we do is plot the time series. I plot the time series here: 24, 26, 28, 24, up and down, up and down. And the stationary is the overall nature of the time series. Well, it goes up and down. There is variability, but it starts here and it ends here, and it's pretty much a level, constant. And so this is referred to as a stationary time series. There may be variability, but the overall nature of the time series is stationary. Next is choose your components. And a component here is cause of variability. What's causing variability? Well, there is variability. Right here is 24 to 26. That's variability. 26 to 28, that's variability. What's causing that? Well, it goes down, then it goes up, then it goes down, up and down. There doesn't seem to be any pattern, any reason, any cause. So therefore, when you have unexplained variability, it's referred to as a random component. Then you select your technique. And here's where the table comes in. Well, when we have a stationary time series with a random component, the technique of preference would be either moving average or exponential smoothing. Let's start with moving average. Okay, moving average is the technique. The next is to estimate your parameters. Well, a parameter for a moving average is called the window of the moving average. And a window simply means this. Since I'm taking an average, I could average all 8 values. And some people do, and some people will. But a moving average says, no, I don't need to average all the values. I want to average just the last few values. And the number of the values that you select to average is called the window of the moving average. Because the window, if the window here is 3, then you're going to average the last 3 values, 6, 7, time period, week 6, 7, and 8, to forecast time period 9 or week 9. And then once you observe something in 9, you move the average down 6, 7, 8, 9, or 7, 8, 9, average that to forecast 10. And so you keep moving it down, called a moving average. Or the window could be 5. So here, if I have a window of 3, I'm going to take the last 3 values, 22, 24, 26, and 22, average them, and my forecast is 24. If my window is 5, MA5, moving average of the window of 5, I take the last 5 values, 1, 2, 3, 4, 5. Take these values down, average those, 25. So notice with moving average, my forecast could be either 24 or 25 depending on the parameter on the window. So just because you have a technique doesn't mean you're going to have a forecast. You can have many forecasts determined depending on what your parameters are. Okay, introductory example number 2, exponential smoothing. We have the same weekly time series. We have a stationary time series and a random component. Well, notice up here the second time series, the second technique is exponential smoothing. So let's look at that. Okay, exponential smoothing, the parameters are something called alpha. So alpha, you can have an alpha of 0.2 or 0.6, for example. And the alpha, the window for a moving average, and alpha for exponential smoothing. In this course, we're not going to calculate it. I'll give it to you. It's given. Now, if you want to go deeper, there are different ways of determining alpha and the window with different diagnostics, but we're not going to get into that in this lecture. So, an exponential smoothing with a alpha of 0.2, the forecast is 24.9. The exponential smoothing with a forecast of 0.6 is 24.5. Well, how do we get it? Well, here's our time series. Here's our alpha, 0.2. 1 minus alpha is 0.8, because alpha ranges between 0 and 1. So my forecast here, the time period in the first week is copied as the forecast in the second week. Now that's to get the algorithm started. Now there's many ways of getting that first forecast. Sometimes it's given, sometimes it's an average, sometimes it's forecasting, sometimes it's regression. For this course, to keep it simple, we'll take the data point in the first time series as the forecast in the second time series. Now that we have a forecast in time period in week 2, we have a time series 26, that's our data. We have a forecast 24, that's our forecast. We have alpha, which is 0.2, 1 minus alpha, which is 0.8. And it's 0.2 times my time series plus 0.8 times my forecast. And that's how I get 24.4. Then I do the same thing here to get 25.12. I go all the way down. Or I could change it to 0.6 and 0.4. And I get a little bit different time series. And I get a different forecast. Introductory example number 3 is regression. So in regression, now I have a monthly time series. So each one of these is aggregated over a month. I plot the time series and I see that the overall nature of this time series is not level. It's increasing in this sense, in this case. So when you say, and components, so this would be a non-stationary time series. Now, a component is a cause of variability. Well, variability that it's talking about, let's insert a line here. There it is. And let's black and make it a little thicker. Okay, what we're saying here is the variability is around some stationary mean. In other words, up here, if this is a stationary time series, well, then there is some average population mean from statistics. The population mean in a time series is referred to as a stationary mean. So this stationary mean, what's causing variability around that mean? Well, the stationary mean up here is random because there is no pattern. But down here, there is a pattern. Early in the time series, it's below. Later in the time series, it's above. So that pattern, when you have a pattern that is increasing or decreasing continuously, that's referred to as a trend component. So we have a trend component, but that's not all. So if I take this and put this through here, we can see that all the values don't lie exactly on that straight line. So there's variability around the line. That variability is unexplained, so that's a random component. So the variability due to the non-stationary nature of the time series is a trend component. The variability around the trend line is a random component because it's unexplained. The technique of preference is simple linear regression, and the parameters are the intercept and slope. And we'll be using Excel in here, and in the homework, in the quiz, homework, and the assignments, I will show you how to use Excel. It's a function, the intercept function with y variable and x variable. The y variables are the time series, the x variables is the time, month. And that's the intercept term, 20.75. And the slope, y variable, x variable, is 3. So if I take the intercept and slope times time period 9, I get my forecast 47.75. Now to be complete, we don't use this much, but to be complete, I went ahead and made a table of all the detailed calculations from statistics to do regression. And then I also show the same values with Excel, and then I summarize those with a regression equation, the forecast equation, and the example with a forecast. Introductory example number 4, seasonal indexes. Again, I plot the time series. Now I have a quarterly time series for 2 years. So every one of these is aggregated over a quarter, and there's 4 quarters in a year. So when I plot this time series, I see that it looks like there's a trend here, but it doesn't keep going. It's not a continuous trend. It goes up, comes back down, and it has the same pattern. So when you have a same pattern that repeats, and it repeats, well, the overall time series is stationary. What's causing variability? What's the components? Well, again, the component is around some stationary mean. Well, when you have a pattern that repeats, and here I have a pattern that repeats, that's called a cyclical component. But the pattern is 4 data points. And 4 data points represent 4 quarters, which is a year. So when you have a pattern that repeats every year, an annual pattern, that's called a seasonal component. So a seasonal component is a cyclical component. It's a special type where the cycle is 1 year. Now, if it's truly cyclical or truly seasonal, then the first quarter of the first year is going to equal the first quarter of the second year because it's stationary. But it is not. It's 26 and 24. So there's a little bit of variability. The second quarter from year 1 to year 2, there's variability. So between the years, there's also variability, unexplained. Therefore, between the years, you have a random component. Therefore, variability within a year is due to a seasonal component, which is cyclical. The variability between the years is a random component because it's unexplained. So within a year, it is explained by a cyclical or seasonal component. Between the years, it's unexplained, so it's random. Well, the technique of preference is seasonal indexes. And here we could estimate the parameters, which are seasonal indexes. But no seasonal indexes are used in this case. So it's a seasonal index technique, but the concept does not always have to use indexes. Here's an example where they don't. So what I'm going to be doing, I say, I know that the seasonal contribution is the same in the first quarter, second quarter, third quarter, fourth quarter of every year. So what I'm going to do is take the first year and put it in the first row, second year in the second row. The reason I do that is now quarter 1 is in the same column for each year. And there's going to be a seasonal contribution, a seasonal component that's the same for the first quarter of every year. Now those two numbers should be the same. They're not. The difference is random. So when you have a random component, you take an average. So if I take this average, essentially, I'm replacing that variability with a central tendency estimate, which is the mean. I do the same thing for the second quarter, third quarter, and the fourth quarter. Well, since I have a stationary time series, those averages then become my forecasts. And that's really all there is to it. So in the future, 24, 34, 43, 55, those are going to be my forecast for the next, for year 3. And there they are. Okay. Now, that's the first pass. Now, let's take a second pass. Let's come back up here. Now, let's take a second pass through these techniques, and let me go a little bit deeper. Start with moving average. Okay, here we go. Page 6. Moving average. In this development, I'm going to emphasize the simplicity of moving average and the power of moving average. First is simplicity. Here I have a weekly time series. If I apply a moving average of 3, window of 3, I average 3, and that average of 3 is a forecast for the very next time period, which is 24. So then I move to the next 3. The average of those 3 then represents the forecast in the next time period, which is 25. So the average of every contiguous 3 is the forecast for the very next time period. So the forecast for time period 13 is the average of the last 3 values for an MA3. For an MA5, it's the average of the last 5 values. And we saw that before. Oops. So down here I plot it. The x's here represent my time series, and the solid squares represent my moving average forecast. So remember, for a random component, you have a stationary mean. And so what the moving average is really trying to do is estimate that stationary mean. But since the sample size is only 3 or even 5, then there is going to be variability. And you can see the variability in the estimates. That's the simplicity. Next, the power. And I'm going to emphasize the power of moving average with 3 different characteristics. The first is impulse response. So here I have a time series coming along 25, 25, 25. And between time period 6 and 7, it jumps to 55. 55, 55, 55. Okay? Let me plot it here. Here's a 25. Between 6 and 7, it jumps to 55. So now let me apply a 3-point moving average. Well, when I have 25, 25, 25, the average is 25. That's simple. But when I come to this jump or step function or delta function, then 25, 25, 55, the average is going to be 35. So for time period 8, it's 35. So right here, when it's 5, 6, and 7, the forecast is going to be 35. Here's 35. And then for 6, 7, and 8, 25, 55, and 55, the average is 45. So for time period 9, there's 45. And finally, when I have all three 55s, it just goes back to 55 again. So notice what's happening here. My time series is coming along here, and I have a significant change in my time series. It changes significantly. When you have a significant change, like a step function or a significant change, that's referred to an impulse. And that impulse is something that's important. You want to pay attention to it. You want to model it. You want to graph it. You want your forecast to move to it. Well, the moving average with a window of 3 does move to it. But once it happens, it takes 1, 2, 3 times periods before it totally responds. And that's referred to as response time. It's responding to the impulse. So the response time of a moving average of the window of 3 is 3. Well, if I have a window of the moving average of 5, and I'm doing that down here, notice what happens here. So once it happened, here's my triangles, MA5. So once it happens, it will respond to it after 1, 2, 3, 4, 5 time periods. So the window of a moving average represents the impulse response time, this response time to the impulse. And that's the impulse response. The faster the response, the enhanced impulse response. So an MA3 has an enhanced impulse response compared to an MA5. That's impulse response. Why would you use it? Well, remember, this time series is, say, your demand, and your forecast is running your operations. So if your demand is up here and your operations is operating down here, well, that difference there is that difference, that deviation, that you're operating at a loss. So if this is demand up here, if this is customers, and here's your service capability, you have lost customers, you have lost sales. You don't have enough capacity to satisfy your demand. Well, you want to reduce that as fast as possible. So the difference between an observed and estimated value, that's called bias. So initially it's going to have a bias, but it decreases that bias to 0. But the enhanced impulse response to enhance reducing the bias is a smaller moving average. You reduce the moving average to enhance the impulse response to respond faster and reduce the bias. Okay, the second characteristic is called noise dampening. Well, here I have another time series. I plotted here. There's my x's, and there they go, boom, boom, boom. And then I have an MA3, which is my squares. I have a MA5 here, which is my triangles here. Okay, now let's, to illustrate this, let's introduce some terminology. The time series here, my x's, the minimum in, see what is this, 12 weeks worth of data. The minimum during this time is 21. Here's 21 down here, minimum. The maximum up here is 25. So this time series goes from 21 to 25. The minimum of 21, the maximum of 25 in these 12 weeks. The lowest and the greatest, okay? And so the difference between 21 to 25, that difference, that magnitude, that amplitude, is used to measure the power of a time series. So the greater the amplitude, the greater that difference, the more powerful the time series. Well, a good illustration of this is if this is a sound is a time series, sound is a physical time series. If the sound increases in magnitude and power, And if the amplitude increases, that just means the volume gets louder. And as the amplitude decreases, the volume gets softer. So in business forecasting, the amplitude is important because the greater the volatility, the greater the amplitude, the more significant that time series is in your forecasting. So let's look at the moving averages now. Now notice the moving average of 3, the minimum is 22, and the maximum is 24. So the time series had a min of 21 to 25, min to max of 21 to 25. The MA3, it goes from 22 to 24. So it decreases that amplitude. So it decreases the power, and that's called dampening. Look at the MA5. The MA5 decreases it even more. So as the window increases, you begin to dampen the time series or reduce the power of the time series. So when do you use dampening? Well, remember, this time series is used to determine your operation, your business operations. And so if you have a small window, then if the time series goes up, your forecast goes up. Time series go down, your forecast goes down. So your forecast will be almost as volatile as your time series. Well, if that's random, and by the way, if there's no real significant pattern in here, it's a random component, which is called noise. Okay, a random component is the same as noise. So when you have noise and there is no pattern, I don't want the pattern. I want to reduce that pattern down to estimate my stationary mean. Well, the best way to reduce that noise or the amplitude of the time series, which is not a signal, not an impulse, is to increase the window, and that will dampen the noise or dampen the volatility of your time series. So it'll stabilize your forecast. So noise dampening will stabilize forecast and reduce the noise. The third characteristic is filtering. Now in filtering, I have another time series here, 21, 22, 26, 21, 22, 26. And so if you notice, every 3 is the same. Every 3, and I repeat. 21, 22, 26, 21, 22, 26. Now if this pattern, so this is a cyclical pattern. Now if this pattern represents 1 year, that's a seasonal component. But this component, which is a cyclical pattern, is a cyclical component. Okay? Well, again, terminology. The terminology down here is that the number of points in a pattern, this pattern repeats every 3 data points. Well, the number of points in a pattern is called the periodicity of the component. So let's bold this and make this big. Here we go. Let's bring it down a little bit. Okay. Is a periodicity of the time. So this cyclical component repeats every 3. So 3 becomes the periodicity of this cyclical component. So let's look at the moving average of the window of 3. So I apply a moving average with a window of 3. I average 3. Now, if I'm using moving average as a forecasting tool, I will apply that average in the very next data point. We've established that. But I'm not using this as a forecasting tool. I'm using it as a filtering tool. So I average these 3, and the average of the moving average used as a filtering tool, you apply it to the middle of the time series, 23. Okay, the next 3, 22, 26, 21, the average is 23. I'll apply it to the middle of that interval, the middle of the interval in the time series. Okay, so now I do this all the way down, and I plot it, 23, 23, and there's my squares. Notice what happened here. It's a straight line. So when I have a time series with a periodicity of 3, I apply a moving average with a window of 3. What happens is that component is removed. It's gone, because the result, there is absolutely no frequency in there. There is no component in there. Removing a component is called filtering. So to filter a component, which is a repeating pattern, the window of the moving average will equal the periodicity of the component. So when the window of a moving average equals the periodicity of a component, then that moving average will filter out the component. And that's what this illustrates. So when would you use this? Well, this is the basis of what we will be using here, called decomposition of time series. We'll take a time series, we'll decompose it into its parts, we'll estimate the parameters, and then put them together to forecast the future. It's a very common technique, very popular, very basic. So we'll do that here and down below before we get done here. Okay. Now before I continue on, let's stop for a minute before we do techniques. And let's ask the question, how good are these techniques once we have one? We have a technique, we have a forecast, let's say down here. Suppose we have a time series here that's a random component. We have moving average of 3. So over time period 13, our forecast is 24. So the question is, how good is 24? How good is that? Well, if it's really good, then we might place a lot of serious decisions on that 24. But if there's a lot of variability, if there's a lot of error, if it's not very reliable, then we're going to be careful using that forecast. So forecast accuracy asks the question, how good is the forecasts? Okay, there's a lot of different metrics. I'll be using these 3 just to illustrate how forecast accuracy is used. Mean deviation, mean absolute deviation, which is MAD, and then the tracking signal. These are the equations. And let me show you how to apply the equations to calculate those techniques. First, assume a window is 3 for the moving average for forecasts. That's what I did here. And there's my forecast. Now notice I'm getting the forecast up here, 24. That's the forecast of 25, 27, and 20. That average is 24. And then 27, 20, and 28, that's in the next time period, 25. Okay, then I say, well, how good are these forecasts? Well, the closer these forecasts are to the time series, the demand data here, the closer they are together, the more accurate they are, the better they are, the more reliable. Well, how can we measure how close they are? Well, simply by taking the difference, D minus F. So this difference here, D minus F, the closer those differences are to 0, then the closer my forecasts are to my demand data, and the more accurate that technique and the more accurate my forecasts are. That's the logic. But again, a lot of people will use all that data, perfectly fine, but I'm only going to use some of it. Again, like a moving average, I'll have a window of 4 for the forecast accuracy measures. So therefore, I will take the last 4 values of my deviations. Okay, let's bring them down here, and here they are. I bring the last 4 values down. The first thing I do is I sum them. I average them, and that's simply the mean deviation with a window of 4. Mean deviation with a window of 4. I sum it, take the average, and there's my mean deviation. So let's interpret this before we go on. Now remember, this is an average of the demand minus the forecast. So on the average, the demand and your forecast, well, let's see, it's negative here. Notice it's a negative number. So therefore, on the average, the forecasts here are slightly above my demand data on the average for these last 4 values. So that difference, again, is bias. So my forecast is slightly above it, so my demand is coming below my forecasts. Well, I have a negative bias. So then my demand is below that, my forecast is above it. So the question is that bad? Is that good? What is that? Well, there's different ways of looking at this. One way is just a brute force way and say it's the magnitude of the bias here is a minus 1.25. Well, the time series up here is 26, 27, 19, 26. So 1.25, the magnitude is about 5% of the magnitude of the time series. So that's fairly small. It's not real small, but it's not bad. It's like reasonable. Okay, so that's just judgment. The second one is the mean absolute deviation. All we do is take the absolute deviation, which means remove the minus sign, sum them and take the average, and that's the mean absolute deviation with the window of 4, or the MAD of 4. Let's interpret that. Let me interpret this with a simple example. Suppose I had a different time series up here, same magnitude, but a little bit different time series, a little bit different forecast. And let's suppose my deviations here were +1, -1, +1, -1. Well, the pluses and minus will average out, so the mean deviation will be 0. So there's no bias. That's perfect. If I take the absolute value, then the MAD would be 1. Okay, well, that's the plus or minus's variability. Time series 2. What if these deviations for another time series was +100, -100, +100, -100? Well, the pluses and minus will average out as before. Again, the bias is 0, which is perfect. But when I took the absolute value, the average is going to be 100. And so there's going to be a lot of variability. Even though there's no bias, there's a lot of variability. So the MAD really is an indication of the variability. It's a measure of the absolute variability of a time series. And a lot of times that variability is used to indicate how much risk there is, the risk in that forecast. Okay, the bias is how much bias there is, and this is the risk for the forecast. Now the third measure is called the tracking signal down here. And the tracking signal simply is a ratio. It's an index. You take the sum of the deviations, which is 5, and divide by the MAD, which is 3.25, which I did right here, which is a -1.53846, and that's a tracking signal with a window of 4, because I did this with the last 4 values. So let's interpret this. And here's where the interpretation where you have mean deviation and MAD combined. Well, the numerator is the sum of the deviations, so that's a measure of bias. The denominator is MAD, which is measure of variability. So it's a measure of bias divided by the variability. So that index, that ratio, that statistic is called a tracking signal. Well, essentially, it is a measure of bias, but it's a relative measure of bias. It's relative to the variability, MAD. Okay? So the bias over here, the absolute measure of absolute bias is the mean deviation. That's how much bias there actually is in the forecasts. The mean absolute deviation is the measure of absolute variability, how much variability. But the tracking signal is a measure of relative bias. It's relative because we standardize it by dividing by the MAD. Well, it's relative to what? As it turns out, it's standardized by the MAD, but it's relative to the window. In other words, it can be plus or minus, but the window represents the limit of the value. In other words, it's relative to a plus or minus 4. It can't be more than 4. It can't be less than a -4. So the window represents the range that the tracking signal can take on. So 0 is perfect. As it starts to go away from 0, you're getting more and more bias, more and more bias, more and more relative bias, more and more relative bias. As you get to a +4 or -4, that's the maximum bias you can have with this measure. Okay, we have a -1.53846. Well, it goes from 0, 1, 2, 3, 4, -1.5 down here. Again, it's not that bad. Less than 1 would be better. 0 is perfect, but -1.5, that magnitude, that's not bad. So that's how you interpret this. So the tracking signal will tell you if that bias is significant. The mean deviation tells you what the bias is, and the MAD tells you how much risk or variability there is in the forecast. So these three illustrate how to use forecast accuracy measures in communication and business. To illustrate this a little bit, to illustrate deviation bias, I have a time series here that starts increasing here. You can see how the differences here begin to increase. Well, that should increase the mean deviation, and it does. 3, 5, 6, 7, 8, 11. Here we have variability that increases, so the variability should be reflected in the MAD, and it is. 4, 7, 10, 15, 18, 24. So all I'm doing here is illustrating what the bias looks like in a graph and a table, and what variability looks like in a graph and a table. Okay. Let's go a little bit deeper in simple linear regression. Okay, in regression here, suppose we are going to forecast carpet sales, and we're going to use housing permits. Well, this is called an extrinsic forecasting model. An example of that is a leading indicator. In other words, we have recognized that carpet sales have increased and decreased by how many housing permits were purchased at the beginning of a building season. If there's a lot of housing permits, there's going to be a lot of houses built and a lot of carpets sold. So we can use housing permits as an extrinsic variable, a causal variable, to forecast carpet sales. So let's do that. The technique we're going to be using is regression. But I want to introduce something else here. I want to introduce transformations. I'm going to transform the carpet sales from square yards. I'm going to transform them to these numbers here by dividing by 1,000. Now that's kind of simple. So instead of having thousands up here, I have it in the units digit. I divide by 1,000. Housing permits, instead of in the tens, I divide by 10, and I've transferred that to the x. So my y variable and my x variable there are transformed values from the raw data. Carpet sales and housing permits. Now the operator I used very simply is just division. The parameter was 1,000 for carpet sales and 10 for housing permits. But the whole idea of transformation is key in analytics, because many complex problems can be solved by finding the right transformation, transforming it into a form that can be solved straightforward. Okay, this is just illustrating that, and we'll see this transformation and formulation in linear programming and optimization and other types of applications. So I plot the data, and here I plot the data. I can see that there is a increase as x increases, y increases. I want to capture that. I'll capture that with regression. So I can regress y onto the x's. If I do that, I get my slope and I get my intercept term. Okay, now at this point, usually I deviate from the course. When I'm in the classroom, I go a little bit more into this description and tell you why I do this. But let me just very briefly, parenthetically, I kind of deviate from the course a little bit, and I go to the real world. In the real world, if I looked at this and I say, look at the variability, it's fairly linear here. Let me just eyeball a line through that. The intercept is 2, and this goes through 8. What is this? This is 10. This is 8. So it goes 0 to 8. 2 to 10 is 8. So 0, 2, 8, and 10, it goes over 8 and up 8. So the slope is 1. So the intercept is 2 and the slope is 1. So that line right there, just by looking at it down here, I can say, I can just say my y equals 2 plus 1 times x. And I'll say I'll just use that as my I use that as my regression equation and my forecasting equation. Is that accurate? It's accurate enough. Is it least squares? No. Is it minimum error? No. Is it optimal? No. Is it good? Absolutely. It's good enough. So in business, a lot of times you'll take these shortcuts called heuristic methods all the time. Now, it's based on the concepts. You don't want to violate basic concepts, but you don't necessarily have to have optimality all the time. So the real optimal value is 1.104. Well, if you're forecasting it, instead of 1.104 is about right here, is that difference going to make that much difference in this variability? No. Well, the slope is 1.664. I have 1 here. Okay, so 1.6 and 1, yeah, it's a little bit off, but is that going to make that much difference? Not that much. Now, if you forecast within this range, this is perfectly fine. As you go outside, sometimes you'll have problems. Again, you'll use the theory conceptually, but know when to use heuristic methods and when not to use them. And that's why it goes outside the purview of this lecture. Okay. But then I go back and I say, okay, well, let's let the x variable be time. You can have a time series as well. Okay. Okay, now let's look at seasonal indexes and go deeper in seasonal indexes. Okay, here I have 12 quarters worth of data. I plot them, and I see every 4 quarters I have a pattern. So again, it's a seasonal component. It's a cyclical component, which is seasonal. Okay, it's a stationary time series, so I would assume there's a stationary mean. So when I have a seasonal component, I want what is called blocking the data. I block it to where I have year 1 here, year 2, year 3, because then I know every column will have the same seasonal contribution. It's stationary, so the difference between the years is random, so I take the average, and that's my forecasts. Again, seasonal indexes were not used. Okay, let's go a little deeper though. Let's take the average of those 4 numbers, and the average here is 30. So let's interpret that 30, which is the average of those 4 numbers. Well, remember, if we apply a 4-point moving average to a time series with a seasonal component with a periodicity of 4, if the moving average equals the periodicity, I will filter out that component. The same thing applies to the forecasts. If I average the 4 numbers here, which is my forecast for quarters 1, 2, 3, and 4, essentially I'm filtering out the seasonal component. So that 30 represents the seasonality removed, or the seasonal component filtered. And this is referred to as the seasonally adjusted forecast, because I adjust out seasonality by filtering it out. So here's my seasonal forecast, and here's my seasonally adjusted forecast. So that 30, 30, 30, 30 is the estimate of my stationary mean. So now I can compare these two. I say, well, you know, when I have seasonality in this first quarter, it's 39. When I do not have seasonality, it's 30. So what does seasonality do? Well, it increases it in the first quarter. Here, it increases it by 9. Well, that's the interval. I can also express that increase as an index. So if I take 39, divide by 30, I have a seasonal index called 1.3, which means that my seasonal forecast is 30% greater than my seasonally adjusted forecast. So seasonality essentially increases the value by 30%. The second quarter, I take 48 over 30 as 1.6. So the seasonal contribution in the second quarter is increasing my seasonally adjusted by 60%. 60% of 30 is 18. 18 plus 30 is 48. Now notice the third quarter, it's less than 1 or 0.9, so it's going to be less. It's a 10% decrease. And finally, my fourth quarter is a 80% decrease, 0.2. So the seasonal indexes down here illustrate the contribution of seasonality throughout the year expressed as an index relative to the seasonally adjusted forecast. So notice how I did this. I took a seasonal forecast equals the seasonally adjusted times the index. Okay? Or I can abbreviate that. The seasonal value is the seasonally adjusted value times the seasonal index. And I say value because I could do the same thing up here in the time series. I could do it in a forecast. Anytime I have a time series, I could do it on any type of value. So let me abbreviate this with SV equals SAV times SI, seasonal value, seasonal adjusted value, seasonal index. And there's three values here. I can give you two and ask for the third. Seasonal value, seasonal adjusted value, seasonal index. There's the equations. Now remember, we got these forecasts without using indexes. But now that we have the indexes, how do we use the indexes? There's some very good applications. On the next page, I have three. The seasonal index application. So here's my seasonal index. Okay, now, suppose next year, application number one. Suppose next year's annual forecast is 400. What are the seasonal quarterly forecasts, or the quarterly season forecasts? The annual is 400. Let's see here. Wait a minute. Let's come back up here. If it's 30, 30, 30 every quarter, then what's my annual forecast? With 30, 30, 30, 30 is going to be 30, 60, 90, 120. So the annual forecast is 120. But down here, this says next year is 400. So if you're in a meeting and you say, wait a minute, the last 3 years it's been 120 for the year. Where'd this 400 come from? And as it always is the case, say, oh, we forgot to tell you. We merged or we acquired some other regions. We've increased our demand. So all of a sudden we're going to have 400 as our annual. So adjust the forecast accordingly for your operations. Okay, I know how to do that because I know what my indexes are. Well, if the annual is 400, then what, and it's stationary, then what's going to be my seasonally adjusted, what's going to be my seasonally adjusted forecast for every quarter? We divide by 4. So it's 100 right here in the graph, 100, 100, 100, 100. So if that's my seasonally adjusted value every quarter, what's my seasonal value? Well, I multiply by the index to put seasonality in. So next year it's 130, 160, 90, and 20. Now the way I like to think about this, I think visually, and if this helps, if you want to put seasonality into a number, you multiply by the index to put seasonality in. If you want to take seasonality out of a number, you divide by the index to take the seasonality out. Well, I want to put seasonality in, so I multiply by the index. And there it is. And so now I know exactly what my forecasts are to run my operations. Application number 2. Next year's seasonally adjusted quarterly forecast is a trend according to the regression equation, 50 plus 10 times t. What are the quarterly seasonal forecasts again? Here we go. So now we're going away from a stationary time series to a non-stationary time series. We have a trend component. And let's assume that our trend is 50 plus 10 times t, where t is 1, 2, 3, 4, to keep it simple. So 50 times 10 is 60, and then 70, 80, and 90. That's my seasonally adjusted forecast. How do I put seasonality into it? I multiply by the indexes. So I multiply here to get my seasonal forecast of 78, 112, 72, and 18. And there's my seasonal forecast for a trend line. So now those quarterly seasonal forecasts have a trend in them. But you can't really see that from the data. But it's there because it's underlying it. So these indexes can really increase a lot of variability or a lot of noise or a lot of power to the time series where you can't see the underlying component. Which leads us to application number 3. The seasonal quarterly time series is given. What is a seasonally adjusted time series? Okay, I plot this time series here, 65, 96, 72, 24. So if you look at that time series there, it goes up and then comes back down. And when I teach this in class, usually I have some stories about this, but I won't do it online. I'll just say, notice that it goes up and it comes down. If it's a stationary time series, and this is 1 year, then the next year it'll be the same 4 values. It'll be just way down here. But suppose you don't have that. You do have some kind of a trend line, but you have seasonality. Okay. If there's a trend in there, well, the trend looks like it's going down, but the trend is going up. Why? Because the seasonal component is so large that it introduces so much variability that it hides the trend component. So if the seasonal component hides the trend component, then, and you want to see it, what do? Then you filter out or seasonally adjust the seasonal component so the trend component emerges. So how do you take seasonality out of a number? You divide by the indexes. So if I divide by my indexes, then the 50, 60, 81, 20, then the underlying trend, you can see it right there, 50, 60, 81, 20. As a matter of fact, it's accelerating. So next year, our forecasts are not going to be down here. Our forecasts are going to be way up here somewhere. So seasonally adjusting a time series is valuable because usually seasonal indexes don't vary much from year to year. Usually seasonal indexes are based on non-business things like weather, seasons, sometimes pay periods, fiscal years, income tax, or whatever. So it's really based on non-business decisions. So therefore, seasonally adjusting it, you can tell how your business decisions have changed your operations. Okay, now let's put it all together. Putting it all together, this is called decomposition of time series. Example 1, I have 20 quarters worth of data. Here's my seasonal time series, and I plot it here. There's my x's. I plot it. Okay. Now when I look at this, I can see here's 4, that's a year, that's a year, that's a year. I have every year, it looks like I have a pattern. It repeats every year. So therefore, I'm going to block it. When you have a seasonal component and it obviously repeats every year, you block it to match up the seasonal contribution for a quarter, for a time period, in this case a quarter. Now the difference between the years is not random. The difference between the years now is a trend component. So between the years, it's no longer random. I don't take the average. I take the trend line. So there's my trend. I regress these numbers onto these numbers. And I can see my trend is 48. Here it's 64. Here it's 28. Here it's 20. Why does it change? Because of seasonality. Because of the seasonal indexes. Because the first quarter of every year, that slope is not as great as the second quarter of every year. See it going up? And the fourth quarter of every year is even less. So the seasonal indexes will change the slope or the trend between the years. Well, since these trends have the seasonal component in them, I can average my trend, and that 40 then becomes my seasonally adjusted trend. My seasonally adjusted trend. Okay, so now from quarter 1, year 1 to quarter 1, year 2, that trend, the seasonally adjusted trend, is 40. So that's my annual trend from year to year. So therefore, I can divide through by my seasonally adjusted trend to get my seasonal indexes. And there's my indexes. So now I know I have a trend here. So I regress this onto this to get my forecast here, which is given here. And the forecasts are plotted up here. And notice they're increasing. Okay, but what happens if I take these values, which are seasonal values, and I divide by my index, then I remove the seasonality. So if I take my time series here, just my time series, for let's say for quarter 1, I divide each of those 5 numbers by 1.2 my index. And I get these values here. That's my seasonally adjusted time series. I take each of these numbers, I divide by 1.6, because that's the index for each of those numbers. I get my seasonally adjusted time series for quarter 2. I do the same for quarter 3 and quarter 4. Now when I plot this time series, which is the squares here, notice my underlying trend line when I filter out or seasonally adjust my time series, the underlying trend line is a nice continuous trend. So now I can see exactly what kind of trend I have. Okay, and I plotted it right here. I took my seasonally adjusted time series, I plotted it right here. Okay, so if I had a stationary time series, I wouldn't have taken the trend, I would take the average if it was stationary. But that's why you plot the data, and you can see that you're going to have a trend line. You can see that there's a pattern that repeats, so therefore I'm going to block it, I'm going to get the trend, and I'm going to get my forecast, and then I can get my seasonally adjusted down here. Now, terminology. This is a quarterly time series. This is a seasonal quarterly time series. This is a seasonally adjusted quarterly time series. Notice it increases by 10 from quarter 1 to quarter 2, it increases by 10. For quarter 2 to quarter 3, by 10. So the quarterly trend of a quarterly time series is 10. The annual trend of a quarterly time series is 40, because there's 4 quarters in a year. But if I take the sum, this is my annual time series. And the annual trend of my annual time series, you notice, is 160, which is 4 times 40. So terminology. So you have to be careful. You can have an annual time series. You can have a quarterly time series. You can have a quarterly trend of a quarterly time series. You can have an annual trend of a quarterly time series. And you can have an annual trend of an annual time. So you have to be careful. Be very precise with language. Okay, but that's example 1. Let's look at example 2. Now, this example 2 is also decomposition of time series. Now, everything, the procedure's the same, the calculations are the same, everything is identical. The only thing different is a different time series. And that different time series, notice here, I have a step function. And this step function, you'll never know it's a step function by looking at the time series. You have to filter it, you have to decompose it, and then plot the seasonally adjusted time series to see the step function. Okay. Now this, putting it all together, is not really part of this lecture. I put it in here anyway. Some people want to do it. Some people want to see it. Essentially what I'm doing here is I have a monthly time series, 12 months in a year. So I have a moving average with a window of 12. If it's 12 months, then 12 will filter out the seasonal component. And I do have a seasonal component. Here's 12 months. Here's the first year, second year, third year, fourth year, fifth year. You can see the pattern is pretty much the same. Looks like a W, 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 W. Anyway, so I filter it out. And so this has seasonality. This has This has seasonality. This does not have seasonality. Therefore, if I divide my seasonal by my seasonally adjusted, I get my index. And so I pull my indexes down here, I average them, and I estimate my indexes for the months. But then I plot this here, and I can regress a line through this and get my intercept and slope. So this is decomposing your time series using filtering. Now, some people ask, when do you use filtering and when do you use blocking up here? Well, notice this is just what is this? 1, 2, 3. This is 5 years worth of data. I think this is 1, 2, 3. This is 5 years worth of data. 5 years worth of data. Notice you're going to lose half a year at the beginning and half a year at the end. So filtering is perfectly fine when you have a lot of data. But when the sample size gets less, blocking is more accurate and a higher quality. Okay, this next page I just described what I did before. Okay, finally, exponential smoothing. The concept of exponential smoothing is a forecast equals alpha times the data plus 1 minus alpha times the last forecast with a smoothing constant. And we saw this in the introductory example. So let's go a little bit deeper. So here's alpha times our data, 1 minus alpha times our forecast. So let's assume alpha is 0.2, and by the way, alpha will always be given. If alpha is 0.2, 1 minus alpha is 0.8. Okay, and so here's my 0.2, here's my 0.8, and over here is my time series, my demand data D. Now, I'm given my demand data, I'm given my alpha, 1 minus alpha. What I don't have is my first forecast. So I have everything I need except this first forecast. Well, like I said before, I take the data in the first time period. I copy it down as the data in the second time period. As a forecast. I copy that data down as a forecast. So now in the second time period, now look what I have. I have my D, I have my F, I have my alpha, my 1 minus alpha. So I bring my D over times alpha, my F over times 1 minus alpha. I multiply, I add. That 202 is my forecast for the next time period. Then I do it again. I bring my D over, bring my F over, multiply and add, and that's 206.6. And then I do it again, and again, and again, and again, and again, and again, and again. And so all the way down to my forecast. Now, exponential smoothing is a moving average technique. But the moving average has equal weights. So when you average it, everything is weighted equally. You can have a weighted average. Exponential smoothing is a weighted average where the weights are exponential weights, where the exponential weights is based on alpha. So the window of an exponential smoothing, moving average, really theoretically is infinite. In other words, for this course, for exponential smoothing, we always use all the data. We would never just use the last two. We use all the data. Okay, so remember, exponential smoothing is really a moving average technique because smoothing in time series analysis is the same as averaging. So when you average something, you take variability and you replace it with a central tendency, so that's smoothing it or averaging it out. And exponential, the term exponential, refers to the type of weights. They're exponential weights. Moving average are equal weights. You can have a weighted moving average. Okay. The power is in alpha. Let's look at alpha for a second. Suppose alpha is large. When alpha gets large, gets very close to 1, then what happens is that this 1 minus 1 is 0. This goes away, and my forecast pretty much follows my data. So when alpha is very large, it approaches 1, it's going to follow the data. Well, following the data is like the same as a short window characteristics of a moving average. And a short window characteristic is an enhanced impulse response. So notice what this says. By changing alpha, you can have the same characteristics as a short window characteristic with moving average, and you can also have the characteristic of an enhanced impulse response. Likewise, with a small alpha, as alpha gets small, really close to 0, this goes away, and it follows the last forecast. So you have a long window characteristic, and it's enhanced noise dampening and stabilize your forecast. So by increasing and decreasing alpha, you can either stabilize your forecast, or you can have enhanced impulse response. Okay, well, traditionally, usually alpha starts fairly low, like between 0.1 and 0.3, for example. It usually starts low, and then will increase if you have some kind of an impulse. How do you know you have an impulse? Well, when you have an actual impulse that's significant, your tracking signal will then become significant. Suppose we had a tracking signal with a window of 4. Well, when your tracking signal is between 1 and 2, then your alpha might be a little bit higher, because you want to follow the data, because you must have an impulse, because you're getting more and more bias. So you can match the tracking signal with your alpha. In other words, suppose your tracking signal was 0. It's perfect. There's absolutely there's no bias. Okay, so really, if there's no bias, then really you want to dampen any kind of noise you have. There is no impulses, because there's no bias. You want to dampen all that noise. But if there is an impulse, you want to follow it, okay, then you'll increase your alpha. So as you change alpha relative to your tracking signal, that's the same thing as something called it's responding to the time series. Okay, and so it's essentially the idea of automated forecasting or artificial intelligence. Okay. And then to go a little bit further, the homework will not be this way, but go a little bit further. Suppose we had, when we look at this, the forecast that we just did, and then we took the error. Notice the error, it's all positive. The error should be plus or minus 0. And also the error is increasing 10, 20, 30, 40, 50, 60, 70, 80. That's not good. When you plot the time series, here's my time series, and there's my forecast. You can see how this, the deviation and the bias keeps increasing. The error increases. Why? Well, first of all, this is a non-stationary time series, and exponential smoothing should be used with a stationary time series. Well, I did this on purpose to show you what would happen. What would happen when you took a technique, when you took this type of time series and you applied that technique to it, where you're going to get a forecast which is down here, and it should be up here somewhere. So this is the idea of having the wrong technique for the type of time series that you have. So in solving a time series in forecasting, know your time series, know your components, know the stationarity before you start using the techniques, and apply the techniques correctly. Okay. But notice for regression, there's an exponential smoothing with 2 parameters. One parameter for the random component, like we did up here, another parameter for the trend component. So you can have a 2-parameter exponential smoothing. Or the 2-parameter could be with a seasonal component. Or you can have a 3-parameter exponential smoothing when you have trend, seasonal, and random. When you have trend, seasonal, and random, non-stationary, you can do blocking or filtering, either one. Well, when you have higher components and more complex systems, here's where you go into the Riemann models, Bok-Jenkins techniques, and spectral analysis. Okay, and this video does not go into those. So to be complete, for those who are interested, I did list the equations, an example of a 2-parameter exponential smoothing, and then finally the equations down here for the 2-parameter seasonal and the 3-parameter exponential smoothing. And then I have a trend analysis using simple linear regression. I put it in these notes, although we're not going to do that. We're not going to go into this now. In other words, you can use linear regression to solve nonlinear problems, certain nonlinear problems. Reciprocal, logarithmic, quadratic, of course, exponential, power series. The power series is called the Pareto relationship, and a sigma-1 function. You can use linear regression. But that's not what we're covering in this course. In this lecture is just an introduction to basic fundamental business forecasting. That's all I have. I hope this helps. Between now and the next time I see you, be safe and take care.